Hello and welcome back. Today I like to talk a little bit about oscilloscopes. I wore my shirt for the occasion, and we're gonna play a little bit with the Juntech, with the Max oscillator. And the thing I want to talk about is about the analog bandwidth and the sample rate. And when I bought my oscilloscope, I just bought one that I thought, okay, it has proper specs and that will be fine. And I just only look at the analog bandwidth because I thought, if it says 200 megahertz, I can measure 200 megahertz. Well, that seemed to be not the case. And I want to do a test to see why that is not the case. And the best way always to do this in practice. So I asked the dealer shop if I can borrow two oscilloscopes, and they were very happy to do that. So I have here the O1 SDS 1022, 20 megahertz, and with the sample rate of 100 mega samples. And I also have here the O1 SDS 1202. That is 200 megahertz and with 1 giga samples per second. And as a comparison, I have also my Sigland SDS 1202, and that is the same specs as this one, 200 megahertz and 1 giga samples. And the Juntech, we can use up to 80 megahertz. And if we go above that, I have here my Max that goes up to 6 gigahertz. Of course, we're not gonna do that on the oscilloscope because we probably see not much. But it is great to see what the difference is between a few specs that are on the oscilloscope. Well, the first one we already mentioned, that is the analog bandwidth, and that is the frequency that's on it. So that says 20 megahertz. So that is the analog bandwidth actually. And that is if you put in a signal, then at some point the internal analog circuit will have some attenuation. And when the attenuation starts to drop, so that purely has to do with the electronics inside. And when it starts to drop more than 3 dB, then they say, okay, that is the maximum analog bandwidth. And then you have the rise time. The rise time, that is how quick the analog and the digital electronics can find a rise of your signal. So when it's at 0, how fast it can detect. Well, that is usually okay because I'm checking here. That is 20 megahertz oscilloscope, and that one can do 17.5 nanoseconds, which equals about 57 megahertz. So that would be enough for the 20 megahertz. So that is good. And if I check here at the O1, that can do 200 megahertz. The rise time here is 1.7 nanoseconds, which is almost 600 megahertz. So nothing wrong with the rise time. I haven't checked on my Sigland, but I'm convinced it is probably good also. And then we also have the sample rate, and that is kind of an important one. Because the sample rate actually means how many samples, and that is the digital side, how many samples it can do in a second. So that kind of translates to also the maximum frequency that it can properly monitor. But that frequency could be completely different from the analog bandwidth that they put here on the top, because that means if we have 1 giga samples here and we do this at 200 megahertz for the full wave, that means we only have 5 points. So in that sense, it is almost like 1, 2, 3, 4, 5. So I think at 200 megahertz you will probably not see the difference between the triangle and the sine and the square, because you only have 5 points. I watched some other videos about that, and I will put the links also there. It's very well explained. But as a rule of thumb, I would just say if you measuring sines or analog signals, 2 to 3 times the frequency would be good enough. So that means for this 200 megahertz oscilloscope that you are probably just below the 70 megahertz that you can probably measure for analog systems. And for digital signals like square waves, they even say you need to do 4 to 5 times even as a rule of thumb. So the sine wave on this highest frequency that you have only 5 samples, you will see that it almost starts to look like a triangle because you just don't have enough samples. And that is really the biggest difference between that frequency and the sample rate. And for a square, it's even worse because that's why they say, but the rule of thumb, you need at least 4 to 5 times. And why is that? Because if you have a square and you do exactly 5 samples, then you also end up with a triangle. So you don't know if what you're looking at. Is it really a triangle? Is it a sine or is it a square? And my sample rate is just too low. And if you go a little bit lower in frequency or you have a better scope with a higher sample rate, then you can do a few samples more. And then it is still not a square, but it starts to look like a trapezium. So you're closer to a square. And these differences I like to show in practice with these setup. I forgot to mention something about the sample rate, which is important. It is the sample rate of the ADC converter, the analog digital converter. And if you have 2 channels, it is shared over the channels. So instead of 1 gigasample, you end up with 500 megasamples per channel. But I'm now measuring on 1 channel only. But you need to think about this, especially if you have a 4-channel oscilloscope. If you then you need a very high sample rate. But usually, if you have 100 megahertz or 200 megahertz, then you already have 2 gigasamples. So, but you need to be aware of that because probably the cheaper models have or a lower analog bandwidth, or the expensive one have a higher frequency, but they have a real high sample rate, and they so probably on very good oscilloscopes with 4 channels you have 2 gigasamples or more. And then there is also something else, but then you need to watch one of the links below. You can also do interleaving. Also, what is very important to know about the sample rate is that you need to know if it's interleaved or real, because if it is interleaved, it thinks you have a high sample rate, but instead of, like, let's say it is like 2 gigasamples interleaved, then you actually have 1 gigahertz ADC converters, and that is very difficult to synchronize. So usually it doesn't get the best result. Then you need to try to look for non-interleaved. And usually this is all non-interleaved. But this one, I suspect that I interleaved it because the processor was around 200 megahertz and they say it's 500. And in the teardown, we saw some delay lines. So what I think that they did, they have just 200 megahertz, and then they apply their smart Chinese spec multiplier, and then they just say, it's 500. So it's actually 2 times 200 interleaved. And that's why the wave is just shaking all around. Okay, let's start with the sine wave at 1 megahertz. As you can see, the 1 megahertz works okay in the 20 megahertz oscilloscope, although you can see a little bit that it is not super stable, but that could also just be the quality of the oscilloscope. Let's see what this looks like on the 200 megahertz. Well, on the 200 megahertz scope, the wave looks a lot more stable, but I see a little bit of distortion here on the top, but that could also just be the display. If you have a look here closer, you see it's already a lot more stable in the corners here. If you compare that to the other oscilloscope, the 20 megahertz. And that has to do purely with the samples, because the more samples you have, the more nice it looks. Yes, and if we have a look at the cyclant, that is, I think that's why you pay a little bit more for the cyclant. That this one is really super stable. The sample rate is exactly the same as the Owen, but you see a lot less distortion on the sine wave. So this is all easy to do for all of the oscilloscopes. Now we just change to the squares, and let's see how they handle that. Well, we have a look here at 20 megahertz oscilloscope, and as you see, it is not that stable, but you can clearly see it is a square wave. There is some overshoot there, but it could just as well be the signal generator. Let's have a look on the 200 megahertz. So you see the square is a lot more stable. We see here a little bit the same, but this could be a little bit the rise time of the signal generator, but you don't see the overshoot. So that is already better. I still think that this wave is a little bit weird, but I think this is just the display. The top looked even better on the 20, so maybe this is a software issue. But the wave looks a lot better, so you can easily see that that the sample rate here is good. Yeah, this is what it looks like on the cyclant. Yeah, it is a bit more stable, but the shape is the same as the Owen, as you can see, but the display is a bit better. It is amazing how easily you already see the difference between the oscilloscopes between the 20 and the 200 megahertz, but that is only to do with the sample rate, because we are well below the analog bandwidth. So here you can already see more samples are almost always better. I don't think it makes sense to do the triangle, because in higher frequency, the sine wave and the square wave will also look like a triangle already. So I don't think that makes sense. We did 1 megahertz. Now I like to jump immediately to 10. Okay, at 10 megahertz. And as you can see, we can see the proper wave, but it already starts to jump a little bit. And that is half its frequency. So that's why I think it is the rule of thumb that for analog, you need to have at least 3 times the frequency you're about to measure. Now we are looking at the 200 megahertz Owen, and as you can see, it is jumping less, but still it doesn't look that stable. I'm almost suspecting that we can probably see better in a higher frequency, that they use maybe interleaving, that they have twice 500 instead of 1 gigasample. So now we have a look at the cyclant, and it's just completely stable. We can go to the squares. Okay, 10 megahertz. Now we go to the squares. Let's see what that will bring. Okay, here we are at the 10 megahertz square. And as you see, it already started to look like a trapezium. And that is purely because of the sample rate. And we can do a little bit like this, and then it looks a little bit more like a square. But this is purely the sample rate, and we are only at 10, and the oscilloscope can do 20. Well, here it's exactly the same, but it looks a lot better because we have a lot more samples. There is still a little bit of the overshoot, but there is a lot more left of the square than on the lower frequency oscilloscope. And the same for the cyclant. Also, that little of overshoot could be the oscilloscope, could be the generator, but it does still look a little bit like a square. Okay, I wanted to go to a higher frequency, but I noticed already at 15 megahertz that the first oscilloscope started to show a sign already. So I have now in the screen all the oscilloscopes and the generator in one take. So now I'm slowly going to raise the frequency from 10 to 15. So 11, 12, 13. You can already see it is now interpolating and thinking it is. Now we are at 15. And now it almost clearly shows a sine wave. And now we can go a little bit higher, and then we can see what the analog bandwidth means. And as you can see, it is now exactly in the middle between these two. So probably below 20 megahertz, you will see it drop. And that is what the 20 megahertz means. Because 16, 17, 18, 19, 20 megahertz. And you see, it is still in the middle. It has the same amplitude, but as you see, it has nothing to do with the signal that we are measuring. So if we go a lot higher, you will see that it starts to drop. Yes, I'm now 21 megahertz, and you see it already dropped a little bit. 22, 23, 24, 25. And now you see it already dropped half. And 26, 27, 28, 29, 30 megahertz. You can still see it, but the signal that you're measuring is not correct anymore. Another interesting thing to see is that on none of the oscilloscopes, and we are only at 30 megahertz, this is a 200 megahertz oscilloscope, it almost doesn't show a square anymore, and the same for the segment. Okay, to rule out that it could be the oscillator, I have here the max. It is max 2870. It starts at 23 megahertz, but we were on 30, so I will put it to 30. Okay, we are on 30 megahertz right now, and this oscillator only does squares out. And you can see it does it a bit better. This one looks like a square. It is a bit bumpy, but it is a square. This one, of course, we are above its sample rate and its analog bandwidth. So this one is not showing that is correct. And this looks a little bit more stable. A little bit zoom in now. So the square is still a square, and we are only at 30. And the segment. So if we go with this rule of thumb and we need at least 5 times, 4 to 5 times, it should be able to do 50. And then we are already at 4 times, but let's see what it looks at 50. Well, at 50 megahertz, we still see a sort of a square wave, but you already can see that it starts to be difficult. Same for the segment. Okay, now I'm going to try 100 megahertz, and according to the analog bandwidth, that should not be a problem. But of course, we are measuring a square, and so we need 4 to 5 times that frequency, and we don't have that. But let's just see what happens. It will probably be very close to a sine. I stop, put my frequency, set it to 100. Point. Here we go. And indeed, it almost starts to look like a triangle. Okay, well, I zoomed a little bit. Yeah, it still is an uneven. It looks more like a sine than a triangle. But here I cannot zoom in anymore. And here I have still one left. But then you can really see how ugly it actually looks. Okay, now we are at 200 megahertz, and I'm already at the limit. I cannot zoom in anymore, and it already see that it starts to jump a bit. I will zoom in. Okay, we are now at 200 megahertz, and as you can see, that it's not much left of our square. Also, I cannot zoom in anymore, so I'm really at the limit of this oscilloscope. And also see it is not that stable anymore. On the segment, I can also not zoom in anymore, but I do see, I can zoom in a bit more than the O1, and it is also not jumping, but the same here, because they are both limited to this 1 gigasamples. Our square is gone. We're just looking at the sine, and it is not. So that's your oscilloscope can fool you by if you have the wrong sample rate. So that was a cool experiment. It was an eye-opener for me, to be honest, because I really thought when I bought my oscilloscope, 200 megahertz, I can measure 200 megahertz. but it turns out to not the case. And we've seen this in the experiment. So for analog signals, just be sure you do 3 times the frequency that you need to measure or you want to measure. So buying an oscilloscope, really look at the frequency. If you're doing digital signals, you need 4 to 5 times because you see how easy it was to make the square disappear and it just became a sign. So that is 4 to 5 times is really the case. And also the sample rate, of course, is important. And also you see the difference already because the specifications on paper are exactly the same. Still, this one is moving a little bit and this one is totally stable. So, but that could be, but I didn't read that deep into the specs. That could be maybe it has interleaving or the software is just different, that it doesn't clean the wave that well. But still, the story is the same. 200 megahertz and we are measuring a square. Well, I don't see a square here. I don't see a square there. So nice experiment. Thank you for watching and I hope to see you next time.